I need you to picture your AI infrastructure as a symphony orchestra, but with an outdated conductor, causing a lot of missed beats. You're gonna need a new maestro. That new maestro is gonna fine-tune every section to harmonize the chorale perfectly. Well, in this training, we will explore a bunch of intelligent quality of service methods that can step in to fix the shortcomings of those traditional approaches like policing or shaping or even queuing, ensuring your network performs like a flawless, well-coordinated masterpiece. Get ready to see how ETS, AFD, and DPP can run network traffic into a symphony of efficiency. I know I started with a bunch of acronyms, but I promise you we're gonna dissect them one by one, and I'm gonna start here with ATS, which stands for Enhanced Transmission Selection. What is it? Enhanced Transmission Selection, ETS, is a component of data center bridging framework used in modern data centers and modern Ethernet networks to improve bandwidth management. How? Well, it enables the distribution of bandwidth across various traffic classes, ensuring that critical traffic, such as AI and machine learning workloads, gets the required network resources while allowing lower priority traffic to share the network without leading to congestion or packet loss. That's the main target here. ETS is going to enable you to allocate a guaranteed minimum bandwidth to a specific traffic class. We're talking here about the AI classes. And if a particular traffic does not fully utilize its assigned bandwidth, the unused capacity can be shared with other classes. If we compare it to traditional queuing mechanisms, the not so intelligent one, we have a hardware queue subdivided into multiple software queues depending on the classes that you have. The most important classes are actually queued, and the most important packets are queued in class number 1, and class number 2 there is for the less important traffic. What happens is you need to also allocate minimum bandwidth per queue. So let's imagine that queue number 1 is actually having a stream of different packets, which is more compared to queue number 2. In other words, queue 1 needs more attention, but hey, you allocated a specific minimum bandwidth and you cannot get more than what you were allocated in case of congestion. And in my example here, X is my minimum bandwidth for Q1. I need more. And the other queue is actually not doing anything. It doesn't need it. Can I borrow some bandwidth that is actually being used by queue number 2? And let me just, who's talking, queue number 1, and let me just get some more bandwidth because I need it. Q2 doesn't need it because it doesn't have a lot of packets. Well, in case of not so intelligent quality of service queuing, that's not going to be possible. Look at the intelligent quality of service or the intelligent queuing mechanism, which is ETS, Enhanced Transmission Selection. It's going to give you that ability. Well, one queue, if it needs more attention, supposedly high performance computing or AI workload, it still can borrow and it still can have some more bandwidth. And it's some kind of elasticity when it needs more attention. That's going to be given to that specific queue if the other queues were not so needy. Since you said intelligence, well, I do have more intelligence to come. Intelligent buffer management. What's that? Well, it's a Cisco feature. Cisco Intelligent Buffer Management is a feature that improves the network traffic handling by optimizing the management of data packets within the switch's buffer. How do you want to optimize is actually how you want to classify your traffic flows. Oh, yes, traffic flows. When a traffic streams into an ingress interface of a switch, modern switches do not have this intelligence to differentiate between the short flows and the long flows, which are very crucial here. Short flows are, in other words, we call them mice flows, and the longer flows or the long flows, we call them elephant flows. What is so special about them, and why do we need to differentiate them and tell them apart? Well, here's the thing. The switch is supposed to be intelligent enough to distinguish those elephant flows that could be greedy in nature and can starve your network bandwidth. How? Well, we're going to know in a few minutes here. But then again, The other hand has the mice flows, and you need as a switch to be, again, intelligent enough to give the mice flows more attention because, hey, the elephants are going to starve your bandwidth and take all the bandwidth that it has, and your mice is going to starve. Maybe that mice flow is actually your most important traffic, which is in AI. It might be the AI workload. So this is where AFD and DPP can come into play. Enlighten me, please. First of all, approximate fare dropping with elephant trap. That's a mouthful, and that's why I prefer using the acronym AFD with E-trap. Oh, what's that? Oh, let's just remember, elephant flows and mice flows. What about elephants? Elephants are heavy. They are going to consume your buffer and take a lot of time until they get processed. Whereas mice are cute and tiny and short-lived. The switch will need to use different parameters to be able to distinguish these two types of flows, such as 5-tuple, and measure also the byte count of the packets to be able to define the flows very accurately. This is what E-trap does at the ingress interface. It's going also to compare the flows against a threshold that you have to define. So if the flow has a byte count lower than the threshold, it is considered a tiny, cute little mouse. Whereas if it exceeds the threshold, it gets classified as an elephant. Then what happens? The elephants need to be separated. This is where you have an elephant table. An elephant table is actually that separate trap where you keep all the elephants. Remember, the main challenge is to prevent elephants from overstaying in that table. When did you arrive and how long have you stayed in the table is the way to measure the danger of an elephant flow. Now, those measurements are going to be passed to the egress interface, where AFD is going to step in. Approximate fare dropping algorithm will calculate when to drop a specific elephant flow. Yes, dropping is involved. If the arrival flow rate exceeds the fare rate that you need to configure, the packet will be randomly dropped from that flow. This will eventually free more space for mice flows that are supposed to represent our AI packets that need to be treated with more delicacy. And then comes DPP, Dynamic Packet Prioritization, which enables the segmentation of these two flows into distinct queues, even if they are within the same traffic class, because hey, a flow or different flows can come from the very same class, but you still need to separate them. Traditional queue management systems cannot achieve this separation due to their lack of flow awareness. So DPP comes to differentiate between mice and elephant flows at the ingress port and then enforce distinct queuing policies at the egress port. That's what's so different between DPP and AFD. AFD just drops the packets, drops those elephants if they remain for a longer time at the egress queue, but DPP is more intelligent. What is it going to do? It's going to give you more choices to treat with those elephants in a different way. I mean, you shouldn't just judge the elephant for just being big or slow. I might just apply a different policy, maybe policing or shaping or different kind of bandwidth allocation. So packets are actually categorized based on flow size into either the mice quality of service group or the original quality of service group of traffic class. The DPP mechanism uses a maximum packet counter to determine classification. If it's being set to n, for example, the first n packets of a flow are assigned to the mice QoS group, while packets from n+1 onwards fall into the original QoS group. So whether we're talking about DPP, AFD, ETS, are considered intelligent compared to the traditional quality of service mechanism that you still can configure. I mean, I'm not trying to tell you that quality of service is not good with its traditional mechanism. We still can use them, but be careful when creating an AI-enabled data center that you might still need some more intelligent mechanisms such as the ones we discussed. I hope that this has been informative, and I'd like to thank you for viewing.